In this segment, I want to talk about Newton's second law. Remember, Newton's first law tells us about what happens if there are no forces acting on it. Remember that Aristotle thought that the natural state of an object is at rest, and if you just leave it alone for a while, then it will eventually come to rest. But Newton turned that idea on its head, right? And Newton says, no, that's not the natural state of an object. Objects will just keep on doing what they're doing unless you push or you pull on them, right? So Newton's first law says, if an object's moving, it will continue to move in a straight line at a constant speed unless you push or pull on it. If it's at rest, it will stay at rest unless you push or you pull on it. So that's what Newton's first law is. Newton's second law really goes nicely with Newton's first law because Newton's second law tells us what do objects do if you don't push on them. To make sure we're all on the same page here and that you're not stuck in an Aristotelian mindset, let's look at this example. A large box is pulled with a constant horizontal force. As a result, the box moves across a level floor with a constant speed. Does the pull have the same magnitude as the weight of the box? Is it greater than the weight of the box? Or does it have the same magnitude as the friction force? Or is it greater than the friction force? Is it greater than either the weight of the box or the friction force? Well, first of all, let's just sketch the box and draw the forces acting on it. Remember that force is a vector, and we should represent those vectors as arrows. There's a dot representing my box. What forces do we have? Well, certainly a pull. We also have friction. Now, we haven't talked too much about friction in this class, but suffice to say that friction is what you feel when you rub your hands together. Friction is the thing that stops this box if I give it a little shove. You're pretty familiar with friction. Friction is also the force that keeps your car on the road. And if you don't believe me, go driving on a really icy day when there's very little friction. Your car has a hard time staying on the road. Okay, we're missing a couple forces here. We have the force of gravity, otherwise known as the weight of the object. We'll go ahead and call that gravity. We're going to talk more about weight here in a bit. And this thing is not just plummeting towards the center of the earth, so the floor must be pushing on it as well. Okay, so those are our four main forces acting on this box. Why don't you go ahead and pause the video and consider this question. I'll see you on the other side. In order for this box to be moving at a constant speed across a level floor, so this is a constant speed in a straight line. If you don't push or pull on something, it will move in a constant speed in a straight line. Now, we have to be a little bit careful. The opposite is true too. If something is moving at a constant speed in a straight line, then we can conclude that there must not be any total force on it. Notice I snuck that word in there, total force. It does not mean that there are no forces at all acting on the object. Take this box, for example. This box definitely has forces acting on it, but the total force has to be zero. And that means that any forces that are acting in the left-right direction must balance, and any forces that are acting in the up-down direction must balance as well. So what can we conclude? We can conclude that the force of the floor on the box must be exactly equal to the force of gravity on the box. We can also conclude that the force of the pull must be exactly equal to the force of friction. So, what's my answer? It has the same magnitude as the friction force. Now, I think a lot of people choose D on this problem because they think, hey, isn't the box going in that direction? If the box is going in that direction, there must have to be some net force keeping it going in that direction. But that's an Aristotelian mindset. That's a mindset that says, I need to be exerting this force in order to keep the object moving, otherwise it will stop. And it's not true, right? The total force on an object has to be zero if the object is moving in a straight line at a constant speed. Here's one more. Here we see a steel ball attached to a string, and it's swung in a circular path in a horizontal plane, as shown in the super sweet figure on the picture. So again, this is a top view of a person swinging a ball around on a string, like this. Woo, okay. At the point P, so that's right here, the string breaks. If these events were observed from directly overhead, what path would the ball most closely follow after the string breaks? Well, why don't you pause the video, think about it, I'll see you on the other side. Okay, well, let's think about what the ball is doing before the string breaks. Is it moving at a constant speed in a straight line? No, it's moving in a circle, right? So it may be moving in a constant speed, but it is not moving in a straight line. Therefore, there must be some force acting on it before the string breaks, right? And indeed there is. That string is applying a force to the ball. That force is directed inward towards the center of the circle. And so that keeps the ball moving in a circle. So that is not an example of Newton's first law. However, once the string breaks, that force that was causing it to move in a circle is gone. What will the ball do in that case? Well, it will move in a constant speed in a straight line. Well, I see 3 different options there. 2, 3, or 5. Which one is correct? Well, what direction is the ball moving in right before it breaks? So as this ball is moving around in a circle, at any point, its velocity will be tangent to the circle. What does tangent to mean? Well, it just means right along the edge of the circle, right? So at this point, the ball is moving in that direction. At this point, the ball is moving in that direction. At this point, the ball is moving in this direction. If the string breaks, then the ball will keep doing what it was doing. It will follow path 2. Newton's first law. Okay, so that's what objects do if there's no forces acting on them. But what do forces do? Forces cause acceleration. And this is Newton's second law. Newton's second law tells us that the acceleration is equal to the net force over m. What does F net mean? Net is just another way of saying total. F net simply means the total force. So the acceleration is equal to the total force divided by the mass. Recall that acceleration is a change in velocity. Remember when we defined acceleration, I told you that it was speeding up, slowing down, or turning a corner. And some of you might have thought, that's weird. Why isn't it just speeding up? That's what I thought it was before I came into this class. Well, now we see why. Because forces cause accelerations. And if you want something to speed up, you have to apply a force to it. If you want something to slow down, you have to apply a force to it. If you want something to turn a corner, you have to apply a force to it. Remember that forces and accelerations are both vectors. Remember that vectors have direction and size, or to say that in other words, direction and magnitude. This is a cause and effect relationship. Forces cause accelerations. Therefore, the direction of the total force is always the same as the direction of the acceleration. Why? Because it's the total force that causes the acceleration. If I drop this ball, the total force on it after it leaves my hand is downward because it's gravity that's pulling on it. What is the direction of its acceleration? Downward. In this picture here, we see this person swinging the ball around their head. The force that's causing the ball to move in a circle is the force of the string. In what direction does the string pull on the ball? Towards the center of the circle. Therefore, what is the direction of the acceleration? Towards the center of the circle. Again, Newton's second law is a cause and effect relationship. Force is the cause and acceleration is the effect. Here's another quick question for you. Here we see, this is the winner of the Triple Crown, I don't know, some years ago. This horse's name is Dear Demi. And here we see a picture of the jockey, the owner, and the trainer. And you'll notice something here. The jockey is far and away the smallest person in this picture. In fact, jockeys are typically very small humans. Successful jockeys tend to be very small people. Do we think this horse would have won if the owner had ridden him? What do you think? Well, most people get on board with this question pretty quickly. No, we don't think so. Why not? Well, because the owner clearly is a much larger human. The owner clearly has more mass than the jockey does. Newton's second law is a cause and effect relationship. Force is what the horse exerts. Mass tells us about how much stuff, and remember that mass is the same as inertia, right? And acceleration is the result, a change in speed. In other words, this horse can speed up much faster with the jockey on board than if they had the owner on board. Now, there's some other aspects here about, the strength of a horse and how a horse runs by jumping and all of these kind of things, right? That also make it so that they won't travel as fast of a top speed if they have the owner on. But thinking just about Newton's second law, this horse will be much slower out of the gates with the owner on than with the jockey. Why? Same force, greater mass, less acceleration. Here's a very large truck and a very small car. Let's say you put the same engine in both. Which one do you think would have the greater acceleration? Why don't you pause the video, think about it, and I'll see you on the other side. Well, it's got to be the car, right? Again, we're creating the same force with the same engine. Therefore, the smaller mass will have the greater acceleration. Therefore, the smaller mass will have the greater acceleration. Looking back at this slide, we could say that acceleration is proportional to the total force and inversely proportional to the mass. It's a cause and effect relationship. Let's do an example. Bobby pushes a 10-kilogram crate with a force of 15 newtons. What is the acceleration of the crate? Ignore all other forces on the crate. All right, well, let's do a quick sketch. Here's my crate. And we have Bobby pushing this with a force of 15 newtons. Okay, what is the acceleration of the crate? Well, Newton's second law says the acceleration is equal to the net force over the mass. Now, in this case, the total force, or the net force, is just 15 newtons, because there's only one force. It tells us to ignore all the other forces on the crate. So, if the net force is 15 newtons, and the mass is 10 kilograms, then the acceleration is 1.5. And what are the units there? Meters per second squared. How do we know it's meters per second squared? Well, I think the easiest way is just to memorize what the standard units are. Our standard unit for force is newtons. Our standard unit for mass is kilograms. And if we use standard units in to our equation, then we'll always get standard units out. Standard units out are meters per second squared. A newton, therefore, is what we call a compound unit. A newton is a kilogram meter per second squared. It's a compound unit. You don't necessarily need to memorize that, but it does help you to kind of keep this stuff straight. It is good to know to memorize what the standard units for these quantities are. Let's make this example a tiny bit more complicated. We've still got Bobby pushing this 10-kilogram crate with a force of 15 newtons to the right. But now his sister Sarah doesn't want the crate moved. So she pushes on the crate with a 10-newton force to the left. What is the acceleration of the crate now? And we're supposed to ignore all other forces. Okay, well, we've got 15 newtons there to the right, and we've got 10 newtons here to the left. What's our total force now? Why don't you make a prediction? Pause the video if you have to. Well, remember that our standard convention is that we call to the right positive and to the left negative. Sticking with that standard convention, we would see that the Bobby is applying a 15 newton force in the positive direction, and Sarah is applying a 10 newton force in the negative direction. So what is the net force? 5 newtons. 5 newtons divided by 10 kilograms is 0.5. Again, standard units in, we get standard units out. Our acceleration is 0.5. meters per second squared. Now, some people might have been tempted to say the total force here is 25 newtons. But if you did that, then you weren't accounting for the direction of force. And remember that force is a vector, so we care about direction. The total force then is 15 minus 10, 5 newtons. A train engine has a mass m. On its own, it can achieve a maximum acceleration of 9 meters per second squared. What is its maximum acceleration when pulling a train car with mass 2m? Ooh, this is a tricky one. We want to use proportional thinking for this. Acceleration is proportional to the force total over the mass. With the engine on its own, it can achieve an acceleration of 9 meters per second squared. So here's my train engine. Okay, here we go. There's my train, and it has a mass of m. We're going to hook that to a train car, which has a mass of 2m. So, before the mass was m, after, the total mass is 3m, right? Because we've got the train plus the train car. So we have 3m afterwards and m before. If we increase the mass by a factor of 3, the acceleration decreases by a factor of 3. Notice this is on the bottom, so it's like dividing it by 3. So, proportional to force, same train engine, same force, 3 times the mass, 1/3 the acceleration. Therefore, the acceleration is 9 meters per second squared divided by 3 equals 3 meters per second squared. A little bit tricky. Here's another example. Despite a very strong wind, a tennis player manages to hit a tennis ball with her racket so that the ball passes over the net and lands in her opponent's court. Consider the following forces. A downward force of gravity, a force of the hit, so the racket hitting the ball, and a force exerted by the air. We call that air resistance or drag if we wanted to be fancy. Which of those forces are acting on the tennis ball after it has left contact with the racket and before it touches the ground? Give it some thought. Pause the video. I'll see you on the other side. Okay, which one of these? A downward force of gravity. Absolutely. Yeah, there's definitely a downward force of gravity there. How about a force of the hit? Ooh. Can rackets exert long-range forces? No, right? The only long-range force we're talking about at this point is gravity. It's not gravity, it's a contact force. And so, if it's contact force, that force does not persist after the contact stops. And so the force of the hit exists only while the racket is in contact with the ball, but not after. So there is definitely no force of the hit. How about a force exerted by the air? You bet, that's definitely there. Our correct answer here is 1 and 3. How about this one? With its engine burning, a rocket in outer space can achieve an acceleration of 30 meters per second squared. If the engine continues burning for a long time, what will happen? Will it accelerate until the inertia equals the rocket force and then continue at a constant speed? Will it eventually slow to a stop? Will it move at a constant speed? Or will its speed increase at a constant rate? Give it some thought. I'll see you on the other side. Remember that acceleration is a change in velocity, which means that if we have a constant acceleration, then we have a constantly changing velocity. How long will this last for? Well, as long as the engine can keep this up. Its speed will increase at a constant rate. That's a little bit tricky, but this brings up a really important point about forces and accelerations. Newton's second law is a cause and effect relationship. It says that forces cause accelerations. Forces do not cause velocity. That's an Aristotelian mindset. An Aristotelian mindset is that in order to keep something moving, I need to keep pushing on it. But that's not true. Forces cause changes in velocity. They don't cause velocity. So I can't just directly tell you, here's a force, what's the velocity? No, I would have to tell you, here's a force, here's what the velocity was, here's how long the force existed for, now what is the velocity, right? So we only know, forces can only tell us about changes in velocity. They can't just simply tell us about velocity. And that's a subtle point. Here's another example. A book is resting on your desk. Consider the following forces. A downward force of gravity, an upward force exerted by the surface. Which of these forces are acting on the book? One only, two only, both one and two, or neither? And if we need a visual, here we go. Here's a book on a desk. What forces are acting on that? Well, let's see. Is gravity acting on it? You bet. Totally is. So we've got the force of gravity for sure, also known as the weight. What else? Do we have? Well, it's not plummeting towards the center of the Earth, right? It's not accelerating downward, so there must be a force upward. It must be the force of the desk. Okay, so we've got the desk pushing up, we've got gravity pushing down. Is that it? I think so. And those are both definitely there. Okay, not too bad. Here's another one. A bowling ball is rolling across the floor at a constant speed. The main forces acting on the ball are a downward force of gravity, a downward force of gravity and a force in the direction of motion, a downward force of gravity and an upward force exerted by the surface, and a force in the direction of motion, or a downward force of gravity and an upward force exerted by the surface. Why don't you pause the video, give it some thought, and I'll see you on the other side. Okay, well, let's see here. We've got the bowling ball. Let's do a quick drawing of our forces. This is the same drawing I had from the previous problem. Let's see if we can just modify it a little bit. We've got gravity, certainly, right? Gravity's still definitely acting on the bowling ball. Previously, we had a book on a desk. Here, this is a bowling ball on the floor, and not much difference between the desk and the floor. Definitely a floor pushing upwards. Is there some side-to-side force? Well, it's moving at a constant speed, right? And so we know that the forces must balance. And so that tells us that the force of the floor on it must equal the force of gravity. Let's say, for instance, that there was a push here. Well, we know that the side-to-side forces have to balance too, since it's moving at a constant speed. So this can't be right. Maybe if there was friction here, but you know what? A bowling ball rolling across the floor has very little friction. And that isn't even an option in any of those. So this can't be right either, because they haven't even asked us about friction. It's not even an option. We can't have friction. If we can't have friction, we can't have that push either. It turns out that this is almost exactly the same situation as the book on the desk. In fact, regarding forces, it is the same. There is a downward force of gravity and an upward force exerted by the surface. And that is it. If you chose C or B, then you are again stuck in an Aristotelian mindset. Because you're thinking that we need to push on it in order to make it move. We don't. It's just going to keep moving, right? Maybe somebody had to push on it to get it moving. I didn't ask about that, right? I told you it was moving at a constant speed. So, however it got moving, that business is over. I'm contending that that motion is the same as this. That seems strange, doesn't it? This is just at rest, and the bowling ball's moving. That's totally different, right? How can the forces be the same? How can the same forces lead to totally different motion? It's not totally different. That's the answer. I told you this is at rest. And it looks like it's at rest, right? It's at rest with respect to my computer, certainly. But you know what? I'm on the Earth, right? I'm in my basement. And my basement is on Earth. And you know what? the Earth is rotating on its axis really fast. You know what? I'm actually moving really fast with relation to the center of the Earth. I'm moving something like 700 miles an hour. It's been about, 20-something minutes since I started this video. That means that since I started this video, this book has moved something like 300 miles. And so, is it at rest? No. It just kind of looks like it's at rest because I am also moving 700 miles an hour. I'm moving 700 miles an hour east. The book is moving 700 miles an hour east, so it looks like it's at rest. So, compare that to the bowling ball. The bowling ball is also moving 700 miles an hour because it's rotating with the Earth. And then something gave it a little shove. Okay, so the bowling ball is moving 702 miles an hour, and this book is moving 700 miles an hour. That motion isn't that different, is it? It makes sense that the forces shouldn't be that different either.